This video, we're going to be looking at sketching graphs, but not just sketching graphs. We're going to find the domain, find the intercepts, and stationary points and more. Whenever a question asks you to sketch a graph in an exam, it usually starts out like this. I call it DISPLAS, but so do a lot of other people, so no one can really trademark it. Why have I written it like that? Let me run that out. Sorry, DISPLAS. So when asked to sketch a graph, you will be asked for its domain, the intercepts, both y and x, stationary points, and their nature. So whether it's a local maximum, minimum, or point of inflection. You find the limits tied into asymptotes, and then finally you will sketch the graph. So that's how I remember using this acronym here. Anyways, let's try one problem. We have a graph of y, it is a function, and it is 27 over x squared minus 27 x. Step 1, find the domain. What can x be, what can't it be? So far on this function, it looks like x can't be 0 because, anything divided by 0 is undefined, so it can't be 0. And it looks like x also can't be, if we look inside this bracket, the other factor, it looks like x can't be the root of 27 plus or minus. Two, let's look at the x and y intercepts. Well, for the y-intercept, x can't be 0 in the first place, so there really isn't a y-intercept. And for there to be an x-intercept, we can set y equals 0, but when we do that, when we multiply out to the bottom, we'll just be left with, well, nothing. So there's no x-intercept either. Now we've got those two out the way. The third thing in the DISPLAS is to look for stationary points. Now to look for stationary points, we know that we have to take a derivative, because the derivative, when it equals 0, we'll find the coordinates of the stationary point. So f dash of x simply going to be via quotient rule, where we let u equals 27 and we let v equals x cubed minus 27x, expanding through the bottom. We'll get a value of, well, not a value, an expression of minus 27 3x minus 27 bracket all over x cubed minus 27x, the denominator, squared. So that'll be our first derivative value here. Now that we have our first derivative value, let's solve so we can actually find the stationary points. We can multiply through the bottom first, so we'll just be left with the numerator being equal to 0. This is the only factor that we really need to care about, so essentially it's just 3x squared minus 27 equals 0, which is just 3x squared equals 27. 27 over 3 is 9, x squared equals 9, therefore x can just be plus or minus 3. So we found our x coordinate of the stationary points. Let's find our y coordinates. Essentially just substitute plus and minus 3. back into the main function above. When we do that though, you'll find that f of 3 is just 27 over 54. 27 over 54 minus 27 over 54. Because remember, our first derivative was that we had minus 27 3x squared minus 27 all over x cubed minus 27x squared. That's where this minus comes from. Anyways, what that means is that that's just equivalent to minus half, isn't it? Simplify that. The y coordinates of when x equals 3 is minus half. So we have a first stationary point at 3 and minus half. Let's substitute in minus 3 into our first derivative to find the next stationary point. You'll find that we'll have minus 27 over minus 54 this time. Minus is cancelled to give us half. So our next one will just be minus 3.5 as our second stationary point. Now that we found our stationary points, you can find their nature. You can do this by, again, differentiating or just taking points on either side and see what the gradient looks like. So keep in mind that these two are our stationary points, and now we're going to look for their nature. For their nature, we'll have to find second derivative, and I'm going to go through quickly the long-winded method of finding the second derivative through calculations, but you can easily just take a few points. So for example, on the number line, if we had the points 3 and minus 3, oh, we got those the wrong way around. All you have to do is just see what the gradient is at 4. So for example, at minus 4 and at 2 and minus 2 and minus 4. So for example, if it's increasing at 4, then it's flat. If it's decreasing at 2, you know that's a maximum. And the converse is also true. So if it's decreasing at 2, then flat at 3, then increasing at 4, you know that's a minimum. At point of inflection, in theory, it's imperfect, but if we check both sides, and it's still flat, still flat, still flat, that's what point of inflection means. So let's run through the quick calculation for second derivative. That being, we can take out the minus 27 from the first derivative, and all we have to differentiate now is 3x squared minus 27 all over x cubed minus 27x squared. This is step 1. If you got here, good job. Next steps, just being careful about the quotient rule really. You can let 3x squared minus 27 equals u. You can let x cubed minus 27x squared equals v for the quotient rule, and therefore you just find u prime and v prime respectively and plug it in. When you plug it in, the first order of operations you should get should look something like this. The minus 27 at that front multiplied by your 6x, which is what you get when you get 3x squared, the first derivative of the 3x squared, you get the non-changing denominator minus of the quotient rule, the derivative of the non-changing denominator. So essentially you have x cubed minus 27x, and you'll also have two versions of 3x squared minus 27, but I'm not bothered enough to write both, so I'll just put that to the power of 2 and call it a day. That is your numerator altogether, but your denominator underneath all of that is of course the x cubed minus 27x squared. Simplifying this down further, sorry I just had a long day today, but maths is fun, maths is cool. You can get 54 3x squared minus 27x squared all over common denominators of x cubed minus 2x cubed and minus 162x over x cubed minus 27x squared. You can further simplify this down by multiplying through by x cubed on the bottom. And after the summation of the numerators, you should end up with a nice simplified result, although long-winded, of a quartic, which is 2x to the 4 minus 27x squared, plus 243, all over x cubed, x squared, minus 27 cubed. And there you go. Now, if you chose this long-winded method, all you have to do is substitute the numbers plus and minus 3. See if your answer is greater than or less than 0. You can pause the video now and do that if you wish. But by my read, when you substitute in 3, you should get a value less than 0. And when you substitute in minus 3, you should get a value of greater than 0. These numbers respectively being 13122 over minus 1574 and 91854 over basically the same denominator. The denominator should be the same. That's how I can tell you didn't mess up. And as we know, being less than 0, that's going to be a max. That's going to be a min, being greater than 0. Now, if you want to sketch the function, you can go ahead. That's the last step of the DISPLAS method. But let's quickly run over limits and asymptotes, may as well. You have noticed that x can't be 0 as it violates the function, and x can't be really plus or minus root 27. So we're going to get asymptotes at these 2 points. So we have x is 0, we have root 27 over here, minus root 27 over here, we can, from the graph, we know what the minimum and maximum points are. We know at 3 we have a maximum. Do we have a maximum? 1 second, guys. Do we have a maximum at 3? Yeah, we do, because it's less than 0. Yeah, it's negative. So that's going to be in the bottom right quadrant like that. Never reaching this asymptote. And at minus 3, we're going to have a flick like this as well. So that's pretty bad. Flick. That's even worse. Okay, we're going to stick with this one, whatever it looks like. Okay, that's a bit better. So here, obviously, -3. Here, we have 3. And yeah, -3 here, 3 there, asymptote here. And you also notice that we never touch the y or x axes either. So beyond root 27 and beyond minus root 27, we'll just have a graph like this, and a graph like this. So the question never really asked for anything beyond that. So if you have something that looks like this, good job, you did well. Thank you for watching the video. Like, subscribe, goodbye.